Let's start with domain restrictions. The general idea here is to find some systematic way of ruling out certain profiles of preferences in order to rule out some of the paradoxes and impossibility results that we've discussed throughout this course so far. Here's the idea. Recall that a social welfare function is just any function that maps some domain, some collection of profiles of preferences, to orderings over the set of candidates or alternatives. And we've been assuming either implicitly or explicitly the universal domain assumption. This just says that the domain of our function f is the set of all possible profiles. That is, D is equal to the set of all sequences of profiles, one for each, sequences of preferences, one for each voter. Now, there's two ways we can think about restricting or analyzing the domain in order to rule out certain paradoxes. The first is to actually go about and restrict which profiles of preferences are admitted into the domain. The idea here is we say that the voters are simply not allowed, or empirically we can argue that they won't actually adopt a certain profile of preferences. I recommend this book by Gartner on domain conditions in social choice theory. There's quite a bit of literature on this topic. But there's another way to think about this problem. A domain restriction amounts to telling the voters that, in some sense, you're not allowed to adopt a certain preference. And this might seem ad hoc or a bit too strong. So another way we could think about this problem is we could focus on the distribution of preferences. We can argue by fixing a particular distribution of preferences that certain paradoxes and impossibility results won't actually arise. For more information on that, I recommend looking at this book, Behavioral Social Choice by Regenwater and his colleagues. Now, in this lecture, I want to focus on one natural domain restriction. So we're going to look at a natural way to restrict the domain of a social welfare function. In order to do that, let's focus on a concrete example. Here's a Condorcet triple. So this will generate an intransitive majority ordering. So note, 2 to 1 prefer A over B. So 2 people prefer A over B, 1 person prefers B over A. 2 to 1 prefer B over C, and 2 to 1 prefer C over A. So this generates an intransitive majority ordering, or intransitive group ordering. So we would like to somehow argue that this profile of preferences should not be admitted into our domain. So why is that? What property does this profile have that would allow us to somehow remove it or throw it out of the domain of our social welfare function? Well, here's the idea. Imagine that all of the voters are ranking the candidates according to one scale, one fixed scale. So the scale might be something like the political spectrum. So people to the left are more liberal and people to the right are more conservative. So once we fix the scale, so candidate A is to the left of B, which is to the left of C, then the voters' preferences, we can represent them by assigning values along the y-axis to each of the candidates. So for example, look at the second voter here. We can assign a value, some value y to the candidate B, some value to the candidate C, and some value to the candidate A. And all that we require is that the value we assign to B is greater than the value we assign to C, which is greater than the value we assign to A. So the ordering of the values that we assign to the candidates has to match the preference, the strict preference ordering of this voter. Now, the actual values, the actual numbers along the y-axis that we assign to the candidates, those actual values don't matter. So we could assign negative values or very small values, or we can make the distance between the value you assign to B and the value you assign to C much greater. Though that doesn't play a role here. All that matters is just the ordinal ranking. The value you assign to B is greater than the value you assign to C when B is ranked strictly ahead of C. Now, we can do that. We can plot the values for voter 1, and we can connect the dots, and we can look at the shape of voter 1's preference along this scale. The scale where A is to the left of B, which is to the left of C. And we can do that for all of the voters. So we look at the shape of all of the voters' preferences, and we can ask what is different or similar among the different shapes. Well, what you can notice is that the green voter, his preferences look different than the other two. The other two have a single peak, and all of the other values fall away from that single peak, or the preference values slope away from some single peak. The green voter doesn't have that property. He has two peaks at the two edges. So the values at these two peaks go towards this minimum value, the value he assigns to candidate B. So there's something different about the green voters, the shape of the green voters' preferences. So does this always happen? Do you always get preferences that look different? Well, let's look at a different profile. And this is going to be a profile that doesn't lead to an intransitive group ordering. So all I did was change for the green voter ranked B in the last place, and I moved B up to the second place. And let's draw the shape of the voters' preferences in this context. And what you can see happened is the green voters' preferences now are single-peaked. There's one maximum value, and all the values assigned to each of the candidates slope down from this maximum value. Now, why is that? Why might that be? Well, we can notice that there is some agreement in this profile that you don't see in the previous profile, the Condorcet triple. Note that everybody agrees that candidate B should not be ranked last, or is not ranked last. They don't agree on who should be ranked first or who should be ranked second, but they all agree that candidate B shouldn't rank last. So there's some consensus in this group of voters. And we can see that because the shape of everybody's preferences is similar. It's single peaked. There's one peak and all the values slope away from that single peak. So does that always happen? So this is the question. If there's a Condorcet paradox, so the group ordering is not transitive, does that mean that somebody has to have a representation of a preference that's not single-peaked? Well, here's another example of a profile of preferences that doesn't give rise to everybody being single-peaked. In particular, the blue agent here ranks C above A above B. So the blue agent is not single-peaked. He has two peaks to the shape of his preferences. And this doesn't give rise to an intransitive ordering. Well, what's going on here is we actually don't have the candidates, the x-axis, labeled properly. Note that if we change the labeling of the x-axis, so now A is to the left of C, which is to the left of B. If we change that labeling of the x-axis, the shape of everybody's preferences becomes single-peaked. Now let's go back to the Condorcet triple. So here we don't see any agreement. People don't agree on that somebody should not be ranked last. Everybody ends up being ranked last. We see in this profile, everybody ends up being ranked in second place. Everybody ends up being ranked in first place. So there's maximal disagreement in this profile. So how can we see that in terms of the shape of the preferences? Well, we've seen that the fact that one of the voters' preferences is not single-peaked might be because of the way that the x-axis is labeled. So let's run through and check all the different ways of labeling the x-axis. So first of all, note that if we just swap the A and the C, the two extremes, that's not going to change the overall shape of the preferences. It's just going to flip them, take a mirror image of them. So if we just swap the two extremes, all we do is take a mirror image, and that's not going to change whether or not somebody's preferences is single-peaked or not. So what matters is who ends up in the middle. So we've looked at the situation where candidate B is listed in the middle. What about when candidate C is listed in the middle? Well, when candidate C is listed in the middle, then the blue agent is going to rank C at the bottom. So the blue agent's, the representation of the blue agent's preference is not going to be single-peaked. And similarly, if we put A in the middle, we see since the red agent ranks A very bottom of his preference ordering, then the red agent is not going to be single-peaked. So let's turn this into a theorem. This is a theorem of Duncan-Black, a well-known theorem. So the definition, the formal or semi-formal definition of single-peakedness says, the preferences of group members are said to be single-peaked if the alternatives under consideration, so all of the candidates, can be represented as points on a line, so represented along the y-axis, and each of the utility functions representing the preferences over these alternatives has a maximum at some point on the line and slopes away from this maximum on either side. So the preferences, the shape of the preferences are going to look like this, or a line that has a maximum value at one side. So everybody's preferences, when you represent the shape of their preferences, you can find some way of assigning the candidates to the x-axis so that everybody's preferences looks like one of these two shapes. If that's the case, and there's an odd number of voters, there's a similar, slightly more technical assumption you need to in order to deal with when there's an even number of voters. But if there's an odd number of voters that display single-peaked preferences, then we can prove a Condorcet winner exists. So by restricting the domain to single-peaked preferences, we can prove that the Condorcet paradox will never actually arise. So the question is, why should we assume that the voters' preferences are single-peaked? Well, I don't have time to really go into the answer to this question, but let me just point you to some literature and throw out a suggestion that has been offered in the literature. Namely, deliberation. When the voters get together and deliberate about all of the candidates, part of the process of that deliberation, they end up having preferences that are single-peaked. So one might see the role that deliberation plays is to form preferences that are in fact single-peaked, and that will rule out some of the paradoxical situations that we've been talking about in this course.